Also, just before I forget, for the folks that are in Zoom today, if you'd like your exam back before I see you next time in class, don't hesitate to ask. Just send me an email and say, hey, Mike, can you scan my exam? Something like that, and I'll be happy to do so. Looks like we can officially start. Welcome back, everyone. Looks like we're missing several people, but I'd understand if people are tired after getting through all the examinations last week and this week. But welcome back. Again, the average grade on this exam was quite high. If we compare that with the other one, I actually forgot what it was. This is 85.16, and on exam one, we had 89.59. So, that's a pretty reasonable drop. It's not by a lot. Exam one was not as bad because this is just the class getting started. So the fact that we didn't change by more than, say, 5 or 6%, I think that's pretty awesome. So congratulations, folks. That represents a class doing pretty well. As far as the exams go, the solutions are always posted. And it doesn't hurt to scan through these sometimes. There was some interesting issues on these that students pointed out. One issue was on the very, very last problem. I was tempted to throw this one out until I graded the exam because, once again, that should have said measure of position, not location. We had a big discussion about that. But I think what happened was I already wrote the exam after I corrected the sample exam and forgot location survived that one time. The good news is nobody lost points on that one, so that's awesome. Doesn't look like that set people astray. Any other questions, folks, on this problem or other problems?
I didn't realize that one, but I know what you're talking
about. Gotcha. The last one was very tricky because this one was a measure of spread. And so we were eliminating the subtract part of the formula and only doing the rescaling times 0.72. Yeah, it's a lot to keep in your head for that part of the chapter, I'd say. But let me pass back another exam. If you have other questions on the exam that you'd like to talk about, don't hesitate to ask. Let me just pick out another one while we're thinking about it. Another issue on the exam that was spotted by another student was right up here. This problem looked awesome at first because I felt like, hey, what a fun way to combine box plots with z-scores. But the trouble was I didn't look too carefully when I copied and pasted in this graphic right here. It should never say data. It should say at least cholesterol to mention the variable. And at best, it should say cholesterol with the units. So sorry about this problem right here. As long as you said something that involved the context, you got full credit on that one. And I didn't look too carefully at 3 complete sentences because I felt like it was already unfair with that issue there. So as long as you mentioned correct things about what you saw here and here, said something about smokers and their cholesterol pulling in the context, then this one was graded very, very lightly. So I think those were the 2 major issues. Sorry for this one. I feel like this is the more serious error right here because that's the whole analysis of data, knowing what the quantitative variable was. And this one was just kind of a distraction that was unfortunate. A lot of people said it is a measure of position / location. So I appreciate that. That was kind of a way to say, I understand that either word means the same thing in that sort of context. But other questions that folks would like to discuss about that second exam?
Yeah, I'm still having problem with number 1C.
Let's take a look at that one.
The mark is the chart.
What percent of the rats did not reject the tumor and had no shock? So when it says right here, what percentage of the rats?
And he says, well, if you can go through the orchestra room and you can.
I don't think that conversation's for us, so let me mute that. So when it says what percent of the rats, we're talking all 93 rats
but
together.
Not rejected.
So did not reject the tumor
no
and no shock would be no reject
and no shock.
No shock right here, 15. Yeah. So we would go the 15 right here, divide by the 93 for 16.1% altogether. Does that make sense on I think the 15 is a harder one because that was an
No, I didn't
intersection on the
right
table.
first. Then I thought I did it wrong.
Oh, I gotcha.
I just was curious.
I think the way I scored these was it was a half a point for numerator, a half a point for denominator. So if you got one off, then you lost just half the credit on the problem. But let me pass back another one real quick. Sorry about that. Oh, I promise I have the exam here. Let me go through it again. Maybe it's slower. There it is. Well, the other thing I'd want to mention on this exam, because I personally do think it's confusing, is the very top page. I usually get the most questions about what I'm always doing right here. So for every one of these exams, you get a fraction for your exam score, the number of points correct out of the 58 points total. But when this gets put into Moodle, that's converted into a percentage. Then the course score right here, this is based off the MyLab. I guess it's officially called MyLab, not MyStats Lab. Your course score is pulling together your MyLab homework, all the quizzes that were due, and then exams 1 and 2. Sorry, question over here? Oh, no, it's Tiffany, right?
Yeah.
Sorry about that. Still memorizing names. That was terrible. Let me get you a correct exam. Sorry. I should probably just double check by calling out the name when I hand these back. But other questions at the moment? Okay, well, as far as the exams go, we're going to repeat the same exact process of how everything came together for exam 3. When we're about this week, you'll see the information filled out. Exam 3 is going to start on, let's see here, looks like chapter 7. So what you did on the very last problem of getting the correlation coefficient, you'll do those exact same steps again, but now you're giving me the equation for the least squares regression line. So that's going to be kind of interesting tie-in after leaving off on chapter 6. And as far as it goes for the third exam, it's just going to depend on the pace that we get through the material. It's probably going to involve chapter 13, chapter 14 potentially, but not too much further than that is what I would expect. Well, I think that's my entire spiel for the exam. Any other questions at the moment, folks? Okay, other reminders is our 7th quiz is going to be due today. That one's an easy one to miss, since if you were focusing on the exam, honestly, that's a good strategy. I don't actually have any kind of late policy, so if I get that quiz late because of the exam, totally reasonable and understandable. I believe quiz number 7 is based off chapter 10, the things that we were doing in that chapter there. And finally, we have a new quiz posted, quiz number 8. Quiz number 8 is on the section on probability. Well, I guess that's a whole chapter. And this one here is pretty similar to what we were doing on, let's see, taking a look at this, probability B or C, only a blood test and a B complement. Looks like this problem is really similar to this one right here, example 6. So we could use example 6 as some motivation for strategies on getting through that particular quiz. But I want to mention again with these quizzes, this is really just a participation credit. I call it a quiz just so it doesn't sound like homework, which is my lab. That means you can work in groups on these kinds of things. You can ask me questions on them, that kind of stuff. So if some of these problems look really vague and mysterious, don't hesitate to ask. I'll be very happy to help out. So that's what we've got going on so far. And then again in chapter 12, we left off right about here, pretty much. This was our last problem on Wednesday's class. Well, any questions at all, folks, before we get started again in chapter 12?
We're starting with explaining the multiplication rule, right?
Exactly, yeah. So we pretty much left off here and then going into the multiplication rule right down below. So the kind of refresh on this problem was, what we're really interested is interdependent events. If you know your events are independent in probability, it affords you a whole bunch of extra ways to calculate that you couldn't do otherwise. The way to think about independence is it has the same kind of impact as disjointness. If you have disjoint events A and B so that the events A and B don't overlap, probability of A or B is just simply add up the two probabilities, probability of A plus probability B. We did that right here when it said digital or audio, although we did make an assumption, assuming those are really disjoint events. Computing the probabilities just meant add them up. That's kind of like what independence does. So here, if we lose disjointness, if these things are no longer disjoint, they have an outcome in common. You can tell that happens when, say, take these two together and the things in common have probability 0.05. That's when the ordinary addition rule just doesn't work at all. You have to use the general addition rule. So by analogy, that's essentially what we're doing with the multiplication formula. There's a really great multiplication formula if you know your events are independent. Lose independence and the formula gets more complicated out of nowhere. So let's do a quick reminder. Independence of the two events, say A and B in this problem, meant whether A occurs or does not occur, the probability of B is the same each and every time. Here, the event A was we were tossing two coins and we got tails on the first flip. Event B is getting tails on the second one, and it's still a 50% chance. On the second situation, A doesn't occur. Probability of B is still a 50% chance. And so this tells us A and B are independent events. Knowledge of one occurring or not occurring did not in any way influence the outcomes of the probability for the other event. But down here on this silly problem, it absolutely did. Whether D occurred or not had a major impact on the probabilities, and so we call these dependent events. So finally, here's how it all comes together. If you know your events are independent, then the probability of A and B is multiplication. You just take all the probabilities, multiply them together. There's got to be an and in this formula, so somehow, some way, that needs to be indicated. Usually the wording just says literally an and, that helps us out. So any questions, folks, with the formula before we take it for a spin? Okay, so again, it's a great formula, but it requires independence to use. And so let's take a look at example 9. It says a survey by the National Center for Health Statistics found that 71% of adults aged 25 to 29 had only a cell phone and no landline. We randomly select 4 25 to 29-year-olds. So independence, well, let's think about it. First, when we say independence as events, you have to say what are the events in the very first place. So that's the challenge on these kinds of problems, just listing events. But if they're randomly selecting 4 25 to 29-year-olds, and we're interested in this information, 71% of them only had a cell phone and no landline, we could combine all this information by doing this. So if there's 4 of them, let A1 say, actually, let's make a sentence go this way so it's not so long. Let's start by saying let A1, A2, A3, E4 denote the events that, so we have 4 25 to 29-year-olds, let's say that here. This will denote the events that the first, second, third, and fourth, 25 to 29 year old has, I'll just abbreviate this to only a cell phone, implying no landline, has only a cell phone. Yeah, what are those? No worries. That was kind of interesting timing.
Yeah.
So Here, that's our one big sentence. I'll add one additional thing. Let's make that a comma and just say respectively. I'm not sure if we've used the word respectively too often in class, but this word is magical because you can imagine if we did this with 4 sentences, you'd say, let A1 denote the event that the first 25 to 20-year-old has only a cell phone. Go down, let A2 be the event that it just becomes kind of dreary. But if you put them all in one sentence and say respectively, then that would mean grab any one of these events, say maybe the third one, it must correspond to the third person that was sampled. So everything in order right here corresponds to the first, second, third, and fourth 25 to 29-year-old. Does that make sense to folks with that word respectively? So with the word respectively, what it says is every one of these 4 events, if we look at them in order, they correspond to these 4 different people that were sampled in the same order. So if we just grab A3, it has to refer to the third one.
Okay.
If we say are focusing on A1, it has to refer to the first person. So it's just a clever way to write one sentence instead of 4 sentences and just save some time writing out. Other questions at the moment, listing out those events? Okay, once we have events, the next thing you want to do is write out their probabilities. But it says right here, a survey by the National Center for Health Statistics found 71% of those adults had only a cell phone and no landline. That's the probability of the events that we're interested in. So now we can say probability of A1 equals the probability of A2 equals the probability of A3 equals the probability of A4, which all is equal to 0.71. Because every one of those events, we're referring to 25 to 29-year-olds having only a cell phone, and the data here says there's a 71% chance of that. So every one of our events has the same exact probability.
Can you see all of those probability of A1 and A2 and A3 and A4 added up together to be 71? If that's what they found in their result?
Well, that's would be, say, referring to just selecting one at random. So selecting one 25 to 29-year-old would have a 71% chance, and it's referring to the entire population of them.
So not 71% of the people they sampled have them, except there's a 71% chance each person will have them.
Exactly. It's referring to more the underlying population. That's a great way to say it, the way you said it just now. Does that make sense with that clarification there? Awesome. Thanks for asking about that. Honestly, that's what makes probability so tricky. There's a lot of implicit assumptions that you have to think about that doesn't always get written out explicitly. So here's all our events. Now, what I would like to do is use that formula right there. The way to use it is we have to decide, were those events A1 through A4 actually independent? Well, it's kind of debatable, but let's think of it in these terms. Probability A1 means there's a 71% chance that the first person has only a cell phone. So let's assume that that really happens. The first person only had a cell phone. Would that affect the chance that the second person has only a cell phone? Some say nay. I would agree with you that probability for the second person having only a cell phone should be the same, 71% chance. We're pulling from the same population, 25 to 29-year-olds. So whether or not this person really had a cell phone or not, doesn't influence whether the second person had a cell phone or not, because we selected them randomly. What would make it dependent? If we went to, say, a household where maybe well, maybe not a household, but maybe if we went to a school where everyone is at about the same social economic status, then if one person did not have a cell phone, we might say there's a lower chance of the others having a cell phone because this is a specific demographic and we didn't randomly select people. But if we're really randomly selecting people in the entire nation, then the outcome for the first person doesn't influence the outcome of the second person, the third person, and so on. So these events would be independent. But does that make sense at the moment? Awesome. So what makes all this work is the population is very large. We're only selecting 4 people. We're not influencing the probabilities at all. So we can say the events A1, A2, A3, A4 are independent. And I have to be completely upfront with you. This is a ton of writing for one problem. When you see how it actually goes, you might think, why did we do all that? Think of all this as kind of the explanation. Notice I never said that this is a real exam problem. I feel like this one is a little bit inappropriate for an introductory statistics class. We only want to do enough probability so we have a good orientation when we do confidence intervals and hypothesis testing. So the resolution to this problem is, what is the probability that all of these adults have only a cell phone and no landline? We're asking for the probability A1 is true and A2 occurs and A3 occurs and A4 occurs. Every one of those is an event that the randomly selected person only has a cell phone. This formula here only works with 2 events, but in mathematics, that's how things are often stated, with the understanding that you can put as many things in there as you like. For just a really quick example, if you think of the distributive law, it's stated this way. A distributes into 2 other things, giving you AB plus AC. And that's much like what's going on here. This is a probability formula with just 2 events. But in actuality, the distributive law could work like this. A times B plus C plus D equals AB plus AC plus AD. A just distributes across whatever you have there. Doesn't matter how many pluses or minus signs you have. The same issue with this multiplication formula. It actually doesn't matter how many events you get. The formula goes like this. You'll get probability A1, probability A2, probability A3, probability A4. This is a lot of writing just to show how the formula actually goes. But once you get here, we're done with the multiplication rule. Any questions, folks, at the moment? Okay, so the big punchline with the multiplication rule is if your events are separated by ands, only ands, then you can multiply together all of those events. Doesn't matter how many, just has to be finitely many. But once we did that, every one of those events has probability 0.71. So this is 0.71 multiplying by itself 4 different times. 0.71, 0.71, 0.71, 0.71 is what it would look like if we route it out in expand form. If we decide to use exponential notation, we'd say 0.71 to the 4th power, because there's 4 different things, 4 factors being multiplied. So that's our probability right there. We just have to throw it into a calculator. But notice what this devolved into. All of this is just a discussion to say how we're getting the result. But when you see this problem in the homework, if you just took 0.71 and rose it to the 4th power, that's the shortcut, and it is hugely substantial. The more probability that you do, the more that this is actually really essential. But we're not doing a lot of probability in our class, so if you know how the problem is supposed to go, no hard feelings if you did it this way in my stats lab. Totally understandable. Well, we're about ready to get a number, but any questions at all at the moment? Okay, let me grab a calculator. So however you do it, if you go 0.71 times 0.71, that would work. If you want to use an exponent, it's a shorthand or just a nice shortcut. It'd go 0.71 to get an exponent in your calculator. It's this up arrow right here, right above the division sign. So go 0.71, up arrow. Your calculator might show it this way, where you're now in the exponent position. Toss in power 4, and that's our probability. It comes out as 0.2541. Forgot to say what to round to on this one, so let's go for 4 decimal places. That's always pretty generically great advice if it's a probability. So 0.2541. Since that's such a long process just to describe how it works, let's say the shortcut is just doing this, writing out 0.2541. Well, any questions at all, folks? Getting to that conclusion? Okay, let's try it out again. Part B says, well, not again, but let's try it to the next question here. Part B asks us, what is the probability that none of these adults have only a cell phone and no landline? If they say none of these adults, that means we're talking about the complement. So we're just going to apply the complement rule and go this way. We want the probability of A1 complement. So the first person selected has no cell phone, excuse me, has only a cell phone, no landline. Then we say and A2 complement and A3 complement and A4 complement. So that's what the probability would look like. Next, we use the product rule, since if the ordinary events A1 through A4 are independent, so are their complements. We should say that right here. These are independent events since A1, A2, A3, A4 are independent. So if the events are independent, so are their complements. And that's just great because now it allows us to take all of this and write down probability A1 complement times probability A2 complement times probability A3 complement times probability A4 complement. Lots of writing just to get that down. So we're just going to multiply some number to the power 4. Sorry, go ahead.
Would it be 0.29 that you multiply to the power of 4?
Absolutely, good call. That's really just the complement rule, right? The complement rule says if the probability, let's maybe put this over here, the probability of A1 or 2, 3, 4, and so on is 0.79, then the probability, let me put down one line, of A1 complement by the complement rule is 1 minus 0.79 for a 0.21 altogether.
So if we know what the probability is 0.2541, why don't we just subtract that from 1? Why do we have to do the 0.71?
That's the thing that's really odd about this, is that that would not be a complement from this one to this one. And let's think of it in these terms. So we have all 4 adults that have only a cell phone and no landline. So let's count it this way. So here's 1, 2, 3, and 4. Hang on, let me think about this. Was a probability that all of these adults have only a cell phone and no landline. So we are involving this one, and this one. You know, I'm starting to get foggy on this question. I'm glad you asked about that. So all 4 have that. If we take the complement of this, we would say was a probability that none of these adults have only a cell phone and no landline.
So they don't have any phone? No cell phone, no landline? I'm trying to figure out why it's not 0.2541. Like, I know it's 0.21 to the power of 4, because that's what that's the complement of that. But why wouldn't you be able to subtract 2.2541?
Yeah, I'm still stuck on that thought right there. So let me think about that.
Instead of proving the answer, trying to prove why that isn't the answer.
Well, let me take a look at part C. Part C was a probability that at least one of these adults have only a cell phone and no landline. Let's see.
And
So-
that word B is word. Well, None of the adults have. So it's basically just asking for the opposite of it. I know.
Yeah, because of the and there, is that what you're mentioning?
Well, none of these adults have only a cell phone and no landline, whatever, no cell phone and no landline. Yeah, I see that.
I see that as well, yeah.
It's fine. That's, context is important in this class. Sometimes it's confusing.
Yeah, for sure. So still kind of stuck on the thought that you mentioned earlier. Let me think about this for a moment. So it's asking, what's the probability no adults have only a cell phone and no landline? And if I take a look at this probability, go 1 minus 0.2541, like you're mentioning, the complement rule on that one, we actually get a really high probability.
Yeah,
But
which is the opposite of what the complement.
we would expect a small probability actually, because the probability of each one of these is 0.21. So let me write down this last thought and see if I can resolve the question that you're asking, the larger question of why does not part A and part B connect with the complement rule? That is a really, really important question. Let me finish off this one right here just to complete the thought and think about that a little bit longer. So every one of these has the same probability at 0.21. This whole thing is being raised to a power of 4. And this is what I would expect for the probability. If there's a really high chance of getting a cell phone and no landline, that's a probability 0.71 given, then having none of the adults having the situation that they only have a cell phone and no landline, that should be a really small probability. And if we go 0.21 to the power of 4, or if folks don't prefer the exponents, you can go 0.21 times 0.21 times 0.21 times 0.21. I think the exponent trick is a little bit better. And we get that value for the probability, 0.0019.
We don't count that 4%.
Not if they're asking for a probability. Yeah. In my class, or for my quizzes and exams, I'm not too worried about that. You could give me 0.19%. Here you could give 25.41%. But in the MyLab homework system, if they ask for probability, they really want just that. So they're really specific. But other questions so far? Oh, that 0.79 came from, it's just hard to see, way at the very top. So the probability of each one of these values was 0.71, or hang on.
Yeah.
Good question. That was a weird value that I grabbed there.
That's like a different number.
Yeah, that should have been 0.71. Thanks for spotting that. I was thinking, yeah, it's up there in the problem. No, it's not. That was a miscopy. So that should have been a 0.71, a 1 minus 0.71. That will revise our answers to a 0.29. And then coming down over here, it's 0.29 to the power of 4. At least we can follow the blue color coding to see where the mistakes are. And then back to the calculator, I'll go the short route. 0.29 multiplied by itself 4 times. Just hit power button, 4. There it goes. And that's the better probability, 0.0071 if we're rounding to the 4 decimal places. So 0.0071. Well, any questions, folks, at the moment? Okay. Now, thinking now once again about the larger question that Madison was asking earlier, let's focus really carefully on these 2 questions. So this one right here was a probability that all of these students have only a cell phone and no landline. And this one right here was a probability that none of these adults have only a cell phone and no landline. Now, the larger question that was asked is, why is this statement not the complement of that statement? So let's see if we could give a really good answer for that. But first, any questions with the 0.0071? Okay, so there definitely looks like there's something weird going on with probabilities. And probabilities is a pretty hard subject, so Not too surprising. If we took 1 minus this answer, way off basis on this one, we were expecting a small probability right here. So let's come down here and expand on this right here. To the best of our ability. What is the probability that all of these adults have only a cell phone and no landline? So this is saying 4 adults satisfy this situation. So if we want to say, get the complement of this, the complement of this event is, well, we just have to negate this statement. We make it false, right? That's all a complement is. So for example, if A1 is the event that the first person has only a cell phone and no landline, then A1 complement is the event that that's not true. The person might have a cell phone and a landline, for example, or more be just a landline, anything like that. We're just negating whatever the statement was. So if you negate this statement, there's in fact several possibilities. Possibility 1 is none, let's say it this way, 0 of the 4 satisfy this event. That would actually make this very true, right? This is saying all 4 adults have only that situation, only the cell phone, no landline. Let me move that down to the next page. A complement is anything that makes this false. And that certainly did have nobody, 0 people having only a cell phone. But there's another way to make that happen. There could be exactly 1 of the 4 satisfying this event. So that would make this false as well. If you're saying just 1 of them make that true. Here, this was exactly 0 of them, exactly 1 of them. We can go down to a new one. Exactly 2 of the 4. I'm going to start using this little device, just quotes to say, same statement above, satisfy this event. And the last one is exactly 3 of the 4, put some quotes, satisfy this event. So every one of those would be complementary statements. The total complement is all of that. And you would have to calculate those probabilities in each one of these situations and add them up. So it becomes a pretty gigantic complement in a weird way. I still think it's kind of confusing, but does that kind of help to see what the logical problem is, taking a complement here to go down to here? Okay, so the gist of it is, when we said all of these adults, we meant all 4 exactly, and there's a lot of ways to negate that event. Any one of these situations negates it. So all of this is the complement. But let's take a look at this statement next. What is the probability that none of these adults have only a cell phone and no landline? So this is saying exactly 0 satisfy this event. That's matching up with this part right here. But the reason it's not a full complement is if we took a complement of this statement, it should have returned these, at least 1, 2, 3, and up to 4 have a cell phone and no landline. So I think that's one way to visualize what's going wrong with the complement, but that is a pretty insightful and complicated question to think about. I think part C helps out a little bit because this one is a complement of something, one of those 2 statements. So to finish up our discussion on the complements of this situation, let's take a look at part C next. Part C says, what is the probability that at least one of these adults, that is a really powerful statement, let's give it yellow, has only a cell phone and no landline.
But for A1, for example, we would do 100. Because that's how we know they have that, but the rest of them are still 71, we don't know.
Well, I think they're all still going to be 71 in this case for the probabilities. So we're not changing the probabilities. But what is changing is that this statement here is a complement to either this statement or that statement. It's kind of tough to see which one it would be, though. Anyone spot which complement it is? Let's see.
Well, it's number 2. Yeah, so exactly one of the 4 satisfying.
So this one says probability that none satisfy, so 0 of them. This one says at least one. So it's exactly. So if it's at least one, that it could satisfy this, or hang on, let me get my arrows going. It could satisfy this one, this one, this one, or that one. So at least one means there could be exactly 1, exactly 2, exactly 3, or maybe even all 4. This one said none of them, which was 0. That's the odd one out. And this event includes that, and that. That one is actually a complement to something. It's a complement to part A in this problem. Not easy to see though. So one thing that I said when we started this section of probability, chapter 12, is when you go to do these problems in my stat lab, if you get stuck on them, could be something like this going on. Don't hesitate to come to class and just say, hey, can we start out class today looking at problem so-and-so in chapter 12? Super happy to do that because once again, we're doing probability just to become familiar with it. We're not going to do hard exam questions on it. The only exam questions were the ones we indicated right on this document at the start of the example. So what's happening on this one is when it says at least one, this is 1 minus the probability that all 4, or hang on, let me see this. Think about this one. So at least one would involve just going through these again to organize our thoughts. This one's pretty tricky for me as well, it turns out. I did this one at the start of class or the start of the day to be prepared for class, but come to class and suddenly it feels more foggy all of a sudden. But that's just how probabilities go, I guess. So when it says at least one of these adults has only a cell phone and no landline, that'd be this one, this one, this one, and this one. So that's the at least one. But we're going over here to the complement rule. So we negate at least one. We go to this one, exactly 0 of them. Let's put that here in a special color because this is hard enough. I'm kind of glad we had this discussion here to help out. Exactly none would go right inside there. That just so happens to be the probability that we calculated up here. So let's just pull this down for a moment. We can now say that this is 1 minus the probability 0.0071. This is giving us a really high probability, but keep in mind the probability of just one person having only a cell phone and a landline was 0.71. This is saying probability of at least 1. So we would take that probability plus that probability plus that one plus this one that we had already calculated, tally them all up. That's a lot of work. Or just do the complement rule. We'll go 1 minus 0.0071. And now we come to a probability 0.9929. By the way, this problem that we did today, or this one right here, I mean, this is very similar to a real problem in my stats lab. So if you see this problem come up and you're not too sure, use this document as a guide to help out, and it could be pretty productive. But finally, that's how this problem ends. Any questions, folks, with the part C? Let me eliminate this one. This one is only to give the probability of exactly none, which is what all these were saying with the complements. So this problem here was independence together with complement rules, lots of them. And it's just, I think, pretty difficult of a probability when you're juggling multiple events, 4 of them, all with the same probability. But looks like we got it, folks. That's how these all come back together. And let me put orange on this one again, just to convey. We got this from part B. Well, it looks like we have one last question in chapter 12 to get through. That one's going to be the general multiplication rule, which is essentially a thought of what do you do when you don't have independence? What's our next recourse? But any questions whatsoever, folks, running through this one? Okay, probably not the world's funnest problem. I almost feel like I owe you all an apology, but we're getting through it. Once we get past probability, it becomes back to like a normal stats class, the ordinary things we've been doing all along. So one last problem, and we're over the hump. This one's kind of one heck of a problem, though. There's something called conditional probability. And my job is to convince you we have done conditional probability. In fact, we did it on exam 2. So as we take a look at this, let me pull up exam 2 so we can put this in a better context. So the place we did conditional probability on in exam 2 was these questions right here on problem number 1. And let me see if I can get a better arrangement of my windows here real quick. Just a small mental break while we organize this. Okay, yeah, just about got it. So here's our good old problem with, well, I guess it was kind of a morbid problem, sorry about that, but a realistic scientific type of problem dealing with rat subjects and whether they were shocked or not, and whether they rejected a tumor. And one of these questions went along this way. Among all the rats that rejected the tumor, that's a condition. That gave us a conditional probability. And what it did was, it took a sample space of 93 rats, and we refined it to a sample space of just the 45, the moment we said, among all rats that rejected the tumor. Let me see if I can actually put a temporary screenshot so we don't have to scroll to see this. I'm just going to put this here temporarily. So there was the data table. And we're looking into part B. Okay, so there it is. So now let's take a look at conditional probability. This is a bit tricky, but really only doing one question on it for the sake of the homework, and then we're kind of done with it. But it'd be rude not to think about conditional probability after doing the multiplication rule, because that rule just doesn't always work. If independence is gone, we need this. So here's how it goes. We assume probability of A is not 0. And that's like assuming that there is not a 0 right here in the reject column. It wouldn't have even made sense. You just have a whole bunch of zeros. It's a weird problem. You should just delete row 1 if that was true. Then it says, when we want the probability of an event from a conditional distribution, we write probability of B given A, and pronounce it the probability of B given A. I guess I just said that again. A probability that takes into account a given condition such as this is a conditional probability. So what's the condition? The condition is right here. So when you write probability of B given A.
In the back, Steve, still. Come on, kid.
Uh-oh. Not too sure how to resolve that, but we'll just help out with the mute button again. So when we see this, B bar A, this is read as the probability of B on the condition A is true, that the event actually happens. So that bar is just a literal saying given A is true. Down here, we said among all rats that rejected the tumor, that was the condition in our conditional probability, giving us the 45 here and the 45 down below. In conditional probability, when we say probability of B given A, we put the probability of A right down into the denominator, which mirrors exactly what we did in part B right here. Then in the numerator, we put in probability of B and A all together. In our numerator, we just put in 8, but that's inescapable shock and rejected the tumor. So there really is an and tied up in that situation there. We're in the two different outcomes altogether, for instance. So you know what, let's actually leave that screenshot there because I think that this is our best tie-in to what conditional probability really is. It's what we did in this problem. So that H right there is this location in the table. And when you grab one cell in the table, you are in fact doing an and in probability. We're saying inescapable shock and reject all at the same time. So that's how conditional probability works. If you're using probability symbols, it feels way more abstract. With ordinary words like this, I think this is why our author does chapter 3 with probability. It's just a way to tie in what you're really doing. So this is a very firm and real analogy. Any questions at all, folks, with the conditional probability so far? Okay, so now that we have conditional probability, here's how it's defined, but we're really not going to use this formula too much. It's just the way you define conditional probability. This might seem a little bit circular, but I assure you it really is not. A lot of hard work and logic gone into this. And the thought is, well, that's just an equation, right? You can multiply both sides of this equation by the denominator, probability of A. There it is. And that leads you to the general multiplication rule. The probability of A and B, when we have no knowledge of independence, is the probability of A times the probability of B, given that A is true. So that is our general multiplication rule. And the hardest thing about applying this is finding this probability right here. Which one is the conditional one? Wasn't so hard right here because when it said, again, among all rats that rejected the tumor, it automatically gave us the condition. We're on this row right here. So denominator was 45. So our major thing we're going to use is the general multiplication rule. And that takes us to our last problem on the notes. Any questions first, folks, with this kind of a long discussion on conditional probability? Okay, so here's how this last question goes. I don't feel like this is a real fair exam question once again, but conditional probability is important. So that's the one reason we're looking at it here. In fact, when we go to inferential statistics in hypothesis testing, conditional probability is something that does come up. So that's one of the reasons why it's here as well. So here's how the problem goes. A 2012 Gallup survey. Gallup poll is just a very prominent polling organization in the United States, and they're usually known for being very, very reputable. They give pretty good numbers. So the Gallup poll survey of a random sample of Americans, adults, found 52% say they do not drink any soda on a typical day. So that's our first event. Let's start by writing down events. They do not drink soda. So what could we call this event? How about just a generic A? Does that sound all right to folks? Let's call this A. Randomly selected American does not drink soda on a typical day. Not saying they have banned soda from their diet, but they don't go out and buy it when they go grocery shopping, I guess is what that would imply. Next sentence says, of those who say they do not drink soda on a typical day, that should feel like saying, among all rats that rejected the tumor, we just got information about the event we wrote down. That's what conditional probability looks like. When it says among all rats that rejected the tumor, we refine the sample space to something smaller. And now it says, of those who say they do not drink soda on a typical day, we're saying the event A is true, that it occurs. We're looking at conditional probability here. 39% describe themselves as overweight. So this whole thing is conditional because we have one event here, and here's a brand new event, just self-describing as overweight. Let's call that event B. Randomly selected American self describes themselves. That's a weird sentence. I guess you could just say describes themselves, but I'll keep it going. Looks like a run-on sentence now. Describes themselves as overweight. And that's actually important when it says describe themselves, because this is a person that's interviewing you, asking questions that works for Gallup poll. And when you give answers like that, sometimes people are reserved about their answers. So they're self-reporting that they do not drink soda on a typical day. That doesn't mean it happens to be true. That's just how they're responding to the survey. And not everyone's going to be willing to self-report that they're overweight. Some people are pretty touchy about that. I'm not. I'm very happy to say I am overweight. There's no secret there. But a person talking to Gallup poll might be a little bit reserved by actually saying that. So the language here describes themselves as overweight is actually pretty important. It's not about whether they truly were or not. It's how they responded to the survey. That was really important. But that's an event B. And when we look at what's highlighted here, we can rewrite that as probability of, well, describes themselves as overweight. That's probability of B. But there's more to that. When it said of those who do not think who say they do not drink soda, that's the given extra information. Again, like saying among all rats who rejected the tumor. So we come down here with a vertical bar. The vertical bar is read as given. This is true. The event A will occur because we said of those who say they do not drink soda. So A goes right there. This whole thing is the conditional probability at probability 0.39. And we have another probability. The probability of the event A was given at 0.52. So now with those two probabilities, the question's about over. They say here, suppose that this survey is representative of the US adult population. What percent of American adults drink soda and are overweight? Well, this question is a little bit tough because when they say are overweight, we're referring to self-described as overweight. And when it says drinks no soda, we're thinking about they said they drink no soda according to the survey. So this isn't the actual reality. This is how people would respond to the survey question. That's the probability that we're going to get right here. So coming down below, we need to answer, what is the probability that the adults drink no soda? That is the event A. It says and in the middle, so let's write out and. Next part says are overweight. That's the event B right here. So we're doing probability of A and B, but there's no independence. So we can't just take probability of A times probability of B, because whether you drink soda or not, and whether you're overweight or not, those things are kind of associated. I was more overweight when I drank more soda, for example. Those are very, very dependent events in actuality. So when we go to do this computation, it's the general multiplication rule. They give us just enough information to do that. So we can write this out as probability of the event A times probability of the event B given A. We just use the formula in its exact format because we called our events A and B. Probably a good call on this problem because that's the thing that's hard, the formula, not knowing what the events are. Then from here on out, we're just multiplying the probabilities together. So once again, when you do this as a homework question, notice how much work we put in just to get to the punchline. the punchline is you just multiply those two together and that's your answer. So once again, think of this as the explanation. You don't necessarily have to do every single step when you do this homework set in chapter 12. If you take the shortcuts and just multiply those together, no hard feelings. I would totally understand. If we were doing an entire class on probability, we would spend way more time on these kinds of things so we could really do it properly. So think of this as a very abrupt and gentle introduction. We're not doing anything too major. This is the major work that explains how it comes together. So next we take probability of A. One thing to watch out for is we can't actually use the percentage. We need the decimal number, 0.52. We multiply by the conditional probability, 0.39.
You're doing just the probability of A times the probability of B of A right now, or are you doing the probability of A and B?
I'm doing the probability of the A right here, and then times the probability of the B given A right here. So really the first step was we started at probability of A and B, but then we converted up to this formula up here on the second step. Then beyond the next step, we're just plugging in numbers for each one of those events. And finally, here's the big punchline. We're going to take 0.52 times 0.39, multiply those together, and we get a 0.2028. So there's about a 20.28% chance that if you randomly select an adult American, that person would say to a survey person they drink no soda and they are overweight. Pretty low percentage. Well, any questions, folks, on getting through that one? Okay, well, congratulations. That's the end of the set. We can't scroll down any further, and that's our entire unit on probability. Probability is really a pretty tough and counterintuitive mad science, I'd say. So if you know you have to deal with this stuff, then you might want to read this chapter a little bit more carefully and look towards Math 3352, where that's the actual full probability class. But pretty much what we're doing here is just an overview. And the major takeaways when we go through the notes are this problem right here is probably our more prototypical, no, not that one. This one came in as a quiz. But this one right here is a very typical exam problem where you're just going to have a random data table and you have to calculate some probabilities. You might use disjointness, an addition rule, or something along those lines. Another really typical exam problem could be something like this one here as well. Again, you have a data table, you're calculating probabilities, very similar to what we did on exam 2, for example. Major things that we'd have to be ready to do are give an interpretation. So you might have a probability that you have to interpret like you did on this problem. And let's see, what else did we do? Another thing that you might have to do is write down a probability statement like these kinds of things here. But again, nothing too major. But any questions at all at the end of this unit? Okay, we'll save these up. And the next thing we're getting into is section 13.1, the sampling distribution model for a proportion. We obviously don't have enough time to go through these notes, but the reason I'm pulling it up is here's our reward for thinking about probability so hard. Really, we've been doing it since chapter 3 in earnest. And when we look at all this information, it's talking about categorical data, proportions. But the miracle that comes up is somehow, some way, we have a normal distribution out of nowhere. These problems are categorical data, nothing quantitative about it. The central limit theorem for proportions says your statistic, the sample proportion of success is p hat, follows a normal distribution when we refer to its sampling distribution. This is one of the most abstract things, more abstract than probability, to think about in our class. But it's one of those things where we start to think about in bits and pieces. This will be the first central limit theorem when we're dealing with proportions, categorical data. And we'll see a brand new central limit theorem when we're dealing with quantitative data, means. All of these give the normal model. So that's, again, one of the reasons why we work so hard in our calculator. We didn't just plug put it away. We're gonna be going back to second vars and use normal CDF inverse norm again for these kinds of problems. But what this is all going towards is we're using all of our tools with probability to put a probability statement here to describe the error in making that estimate, where P is the parameter, the unknown, and P hat is the statistic that we do calculate. So we'll take a look at those ideas when we come back on Monday's class, since obviously even opening the notes in 5 minutes is not a good idea. We're just browsing what we're about to do. Any questions at all then, folks, before we call it a night officially?
That's chapter 13.
This is 13. In fact, it's just 13.1. The PDF.
Yeah.
That is really
Oh,
weird.
no,
I scrolled down to this
That's
part of
why.
the PDF. Oh, gotcha. You know, now that you mention that, PDFs can be weird. See how there's a hat right here on P hat? If you open this up on a phone, that might not show up because sometimes the actual level of zoom on your PDF affects what you can see and cannot see. Let me see if I can make it go anomalous. Does look pretty good.
Was that bad, Louis?
Sorry, say again? Must have been an open mic. Other questions at the moment? Okay, well, that's all I have for folks today. Have a great night, folks. And we'll be right here in section just 13.1 next class. So when you go to do the reading, I'd say don't read all of chapter 13, just go for the first section. We want to do this one in chunks.